Today we will continue our passivation, but today we will see the passivation. The subject will be passivation and mixed potential theory. So, we will see some of the practical examples where mixed potential theory as well as passivation both will come in picture. Now, we have seen that when you have a cathodic reaction along with the anodic reaction and the metal which is showing anodic reaction or the dissolution reaction, that cathodic reaction actually takes the potential of the metal which is which is basically dissolving to a potential depending on the cathodic reaction, either to active region or to a passive region, or it can be in the unstable passivation region. So, we have already seen this example that if you have a passive metal like this, where you have started with a freshly prepared surface in an electrolyte, and then in case your cathodic reaction is or cathodic polarization is going along this line where it cuts only this portion, then it would attain complete passivity. And if the cathodic reaction is going along this line during the polarization, this will cut the anodic polarization line at this point, and then if it cuts like this, then it would be a sort of unstable passivity. And that case we have already seen that what would be the experimental curve in all those three cases, because when you do experiment, that time you are taking the potential of the metal to a higher potential, or you are actually doing anodic polarization. That time the actual potential curve with respect to log I would look like, in the first case this is, let us say, first case, this is second case, and this is third case. First case it would look like this, because actually you have to see the difference in currents or difference in current density between cathodic current and anodic current. Now, this is in the first case where this would be your E core. Now, in the second case, this is first case, in the second case it would look like, so this would be my reference point where the system will reach to this level if you leave it free, because that time this would be your reference point for the polarization, and polarization will be above this point and below this point. So, this would be my new equilibrium point where the rate at which electron consumption is taking place would be equal to the rate at which electron generation is taking place because of anodic reaction. That case my curve would look like this. And another case, it would be this case where you have three reference points. So, your polarization curve will look like, so I am just extending these 3 points. It would be like this. So, this is cathodic. We have seen that this part is called cathodic loop. Now, during mixed potential theory, we have to see that where this cathodic polarization line is crossing the anodic polarization line, and this is case 2. and this is case 3, where you are attaining this cathodic lobe because this cathodic polarization line is cutting at 3 positions, one at completely passive region, one at active region, and one at unstable region. But when you consider some of the examples where you will see that effect of mixed potential theory and as well as passivation, and then you will see that actually this cathodic polarization line will decide whether the system can reach to this passive region or not. And from engineering point of view, this point is very crucial, because we have to reach to this level, so that I can attain passivity, so that I can control my corrosion current, or we can reduce the corrosion rate to a great extent. Now, in titanium, intentionally palladium or platinum are added. These are very noble metal, highly noble metal, having highly noble characteristic, and titanium is very active. Initially, either this or this, they are mixed with titanium homogeneously. It is basically alloy form. Now, then we will see the advantage of titanium and palladium and platinum on titanium, and this advantage, main advantage, will come from this noble metal because of attainment of passivity due to the cathodic polarization. Now, in case of titanium, if you see its polarization, anodic polarization in acid, in air free acid, it would go like this. It will have active, passive, and transpassive transformation. This is E versus log I. Now, when you have titanium, let us say this is my titanium and platinum. It is a uniform homogeneous mixture, and that is in alloyed form. Now, if you dip it in the acid, now if there is homogeneous corrosion, then since platinum is noble compared to titanium, there would be a sort of phenomena. That phenomena will be discussed more by Professor Chaudhary. It is a kind of de-alloying phenomena will take place, where initially both will dissolve, but later on, since platinum has higher reduction potential, it will again redeposit back. So, in the beginning there would be uniform corrosion, finally there will be uniform corrosion, and after some time there would be platinum enriched zones. These are basically platinum enriched zones. These are all platinum enriched zones. Now, initially the cathodic reaction that is taking place is hydrogen evolution on the titanium surface. Since it is an acid medium, so that case, situation like this, where this is my hydrogen evolution on titanium surface, bracket titanium, and my corrosion rate would be this one, corresponding to IA equal to minus IC equal to I core, corrosion current density. Now, once you have this situation where after some dissolution you have redeposition of platinum on the titanium surface. Now, you will have that effect of higher exchange current density of hydrogen on platinum surface. The hydrogen I0 of hydrogen evolution on platinum surface is very large compared to I0 on platinum. So, what would happen? This point will shift to this point. This is 0, let us say 0 volt. Now, from there my polarization line will start, but since you have this reaction also going on parallelly on the titanium surface. So, finally you have to see what would be my total cathodic reaction rate. My total cathodic reaction rate would be, this is my cathodic reaction on platinum, and you have to add this thing. So, after adding you have to see where would be my total cathodic reaction. Fine. Now, total cathodic reaction is given by this red line. Let us say this is my IC on titanium surface and this is my IC on platinum surface for this hydrogen evolution reaction, and the red one is, this is IC titanium plus IC platinum. Now, you see, initially when there was this reaction only, it was cutting in the active zone. Now, once you have this platinum enriched zone, because of dealloying and redeposition of platinum, your equilibrium point has shifted to this. So, now you see, initially you are in active region. Now, because of this platinum enrichment on the surface, your corrosion current is now this one. So, this one is my new corrosion current I A equal to minus I C, I would say total, since this red curve line is basically the total of I C on titanium and I C on platinum, equal to I cor, and this is in log scale. So, once you have this platinum enrichment, your I corrosion is going to the level of passive region. So, you are attaining stable passivity. So, your corrosion rate of titanium will reduce to a great extent. This is one example, and here we are using the mixed potential theory because we are following the two postulates of mixed potential theory. One is there could be n number of cathodic or anodic reactions, and at the same time there should be equilibrium or the equal rates for electron consumption and electron generation. So, this is that point. This is, and that is what, if you add this platinum or platinum, the palladium effect also will be same, because hydrogen exchange current density on palladium is also very large compared to the hydrogen exchange current density on titanium. So, you are attaining stable passivity. So, this is a sort of advantage of adding noble metal in titanium. But there could be, so this cannot be straightforward that every metal, if you add titanium or add platinum or palladium, you will get the same effect. That means, you can achieve the passivity, but it may not be. For example, the case 2 where I have iron and there I am adding a noble metal platinum. Then it is a homogeneous mixture of iron and platinum. Now, if it is exposed to air free acid, then your cathodic reaction would be hydrogen evolution, and the same thing will follow. you will have in case of titanium, again you will have platinum enriched zones on the iron surface. So, you have this situation again, this is now iron and on the surface you have platinum enriched zones. Now, again in case of iron you have also this kind of situation. This kind of situation, it is also an active passive metal. This is E, this is log I. But in that case, initially the hydrogen evolution reaction is taking place on iron over the entire alloy. So, that case my hydrogen evolution reaction, this is 0 volt and the I0 position is here. This is iron platinum alloy. I0 position is this one. So, I will get the polarization, we have to see the polarization cathodic as well as anodic polarization, and this is my line where I get I core equal to IA equal to minus IC. But once you have this situation, then IH half H2 on iron platinum less than I0, this is I0 exchange current density for hydrogen on titanium on platinum. So, very large. So, this point will shift to this point, but voltage will not change because it's we are considering the same reaction. And then accordingly we have to also see that what would be the total cathodic reaction rate. So, this is my cathodic reaction rate on platinum, this is my I0 H half H2 on platinum surface, and this line gives me the idea, gives the cathodic reaction rate on platinum. So, what would be my total cathodic reaction, because here also this reaction is still going on. So, my total cathodic reaction would be, you have to just add this two. So, this is my total cathodic reaction, the red one, total cathodic reaction rate rather, because this is the relation between E and small I, which is the current density, and current density is nothing but the reaction rate. What would be my new equilibrium point, where we have IA equal to IC? This is my new equilibrium point, where this is my I core equal to IA equal to minus IC total. And here you see this is much higher than this. So, here though you are getting positive effect because of an addition of noble metal, that is platinum in titanium, in case of iron it gives the negative effect, because if you add platinum, because the position of this point with respect to the anodic polarization plot for iron in the air free acid. So, here after this situation, dealloying and platinum enriched zones on the iron surface, my corrosion rate of iron or that alloy increases very much. It increases to a great extent, because this is in log scale. So, here it gives a negative effect. This is case 2. So, that means depending on the position of this cathodic polarization start point and the polarization curve for the active passive metal, noble metal addition can be advantageous, it can be disadvantageous. So, in case of iron, we should not add platinum, because if we add platinum, we are going to increase the corrosion rate. Now, this is one. Now, case 3, let us also have 2 more examples. Now, one example is case 3. Now, if you recall that we see that the effect of velocity on the corrosion rate of active metal, if it is totally activation controlled, let us say in case of zinc, that case my corrosion rate and this is velocity. As you increase the velocity of the solution or as you increase the turbulence in the solution, in case of active metal like zinc, it is a flat kind of thing. It remains constant, corrosion rate remains constant if it is activation controlled only. But if it is concentration polarization controlled for the cathodic reaction, then that case my situation would be like this, where as you go higher and higher velocity, your corrosion rate would initially increase, but after some time it will become flat. And if you see the mixed potential theory corresponding to these 2 curves, then one situation your curve will meet like this. This is E versus log I, and this is anodic polarization, this is cathodic polarization, and it is meeting here. So, this is my corrosion current. And second case where you have corrosion concentration polarization controlled, this is activation polarization, that is why we call it activation controlled. And if it is concentration polarization control, that time I will have this situation. So, 1, 2, 3, 4 velocities. As we increase the velocity, you are going to decrease the delta, which is the boundary layer thickness. If you decrease the boundary layer thickness, you are going to increase the IL, and IL is nothing but this at different velocities, and V4, V3, V2, V1, and V4 greater than V3, greater than V2, greater than V4, V1, and accordingly IL4 greater than IL3, greater than IL2, greater than IL1. Now, if you see that up to level 3, that means if you increase the velocity to velocity V2 up to 3, third velocity region, you see that gradually it is increasing corrosion rate, because the corrosion rate is nothing but the point where cathodic as well as anodic polarization lines are cutting. But once you cross V4, it will always cut in the active region, and now after that you keep increasing velocity and keep increasing IL or the limiting current density, you are not going to have any effect on the corrosion rate. So, corrosion rate will be flat. So, up to this is up to V3, and after that V4, V5 you are going to have a constant corrosion rate, because that time always this anodic polarization line will cut the cathodic polarization line in the active zone, in the flat zone, this zone. So, now we have this situation. There we saw one type of metal, it can show this kind of variation. Let us say this is my corrosion rate. There I can have this situation. Initially it will increase, and then after reaching some value, critical value or some value of velocity, it will suddenly drop, and then after that you will see that it is almost constant. So, what could possibly be the reason for this phenomena, where this is my velocity? And in order to understand this, that time I mentioned that we need to understand the passivation. Basically, this curve relates to 2 phenomena. One is concentration polarization for cathodic reaction plus passivation. So, these two things will combine together and then give you this sort of corrosion rate. How do we do that? Let us see that example. Let me draw it on top of this. Again, this potential versus log I. Now, I know the position of anodic polarization line of that metal. That metal, let us say particular metal M, its situation is like this. Fine, this is my active passive metal. Now, I have the cathodic reaction. Let us say my cathodic reaction is starting from here, and I have, this is my activation part of that polarization for that cathodic reaction, and then I will see that once I reach to a value, I value, where if I find that cathodic concentration polarization is starting, so I will reach to the level of IL at that velocity. So, this is my IL1. IL1. So, what would be my corrosion rate? Corrosion rate would be this one. So, let me go there and start plotting that. That case my corrosion rate would be, let us say, this. Let me put it in red color just on the side of this. This is my corrosion rate, corresponds to this. Now, I increase the velocity. As I increase the velocity, IL would increase. So, I can reach to the less level. So, that case this is IL2, this is my corrosion rate, because that point I have IL I core equal to IA equal to minus IC. So, this I would further increase the corrosion rate, because I see that there is increase in current density from here to there. Now, I can further increase the velocity or the turbulence in the system. So, I can reach to this level. Now, the point is, I am cutting this active polarization curve, anodic polarization curve at 3 positions. One position is this, another position is this, another position is this. So, it can either remain here, it can either go there, or it can either go there. So, it is cutting in the passive region, in the active region, and also in the unstable region. Now, the point is, we have started with freshly prepared alloy or the metal. If it is freshly prepared metal, then the anodic polarization will happen on the basis of the cathodic polarization. Now, the cathodic polarization is cutting the line first at this position, because now it is already in active state, there is no surface layer. If there is no surface layer, until unless the material reaches here, the metal reaches here, it cannot form any passive layer it cannot have any passive layer on this metal. So, it will still remain active. So, that case, if you start with a fresh metal, then my corrosion rate would be this point, and other 2 points will not be considered. So, my corrosion rate again I am increasing. So, my corrosion rate would be this. Now, as I keep increasing, I see that these lines, this cathodic polarization line is cutting at 4 different positions. Let us say this point, say again I am increasing, because current density is increasing, this point current density is increasing, this point current density is increasing. Now, at this point, now I see, you please this point is very critical, because this point I L equal to I C, I critical, not C, it is a critical. I critical, that means this is also corresponding to I critical of that cathodic current density. So, this is a very, very crucial point, because at this point I further increase it to this. So, if I add it up, I am seeing that corrosion rate is increasing with the progress in velocity, and at this point I have this point correspond to this, because that point only gives you the rate of electron production generation would be equal to the rate of electron consumption because of the cathodic reaction. Now, see, if I increase the velocity little bit, so I am changing this plot little. Increase the velocity little bit, I see that this cathodic polarization line is cutting this anodic polarization line at this point. So, if it is cutting at this point and it is not cutting anywhere, this curve, let me put it the red one, this is my critical and this is my, this red one is the velocity, which is this velocity, let us say this velocity is 1, 2, 3, 4, 5, 6, 7, 8, velocity 8 is greater than velocity critical. This is basically correspond to velocity 8. Now, at once this velocity is attained, I see that this cathodic polarization line is cutting the anodic polarization line in the passive zone, this zone, and it is not cutting anywhere. And since we have started with a freshly prepared surface without any surface oxide layer or the surface film, initially it will keep increasing, but once we have this situation, we will suddenly go to the passive zone. So, once we go to the passive zone, what would happen? My corrosion rate here, it was this, correspond to I critical. Now, once we increase the velocity from V critical to V8, I will come to this point. Now, if you compare these 2 points, it is having very, very low corrosion current. So, I will reach to the level, this is my new corrosion current, I core, and I am putting P here because this corresponds to the passive zone, and this would lie between second point and third point. So, the second and third point, this is my third point and this is my second point. So, it will immediately drop to this point, and this point corresponds to I core passive. And after that you keep increasing the velocity, what will happen? This will always cut at this point. So, my corrosion current will always remain constant. So, the corrosion rate would be constant after that. So, this is actually what is happening if you have both this combination, and accordingly we can explain the other graph what we have. We had what we could not discuss, we could not explain at that moment. So, this is the explanation for this to happen, and the mixed potential theory actually explains this. Thank you. Let me give one more example, case 4. Let us say you have a metal which is active passive metal, where you have your polarization plot. If you do anodic polarization for that, E versus log I, and that case my polarization plot would be like this. Now, this active passive metal you have in that particular aqueous medium or electrolyte. Now, along with that you are adding, in that case you have cathodic reaction which is coming from some oxidizer, and let us say you keep adding the oxidizer into the solution. That means we are basically increasing the concentration of oxidizer in the solution. So, that case I can have this relation which is ox red, the Nernst equation E0 oxidant and reductant plus RT NF ln ox red. Now, if you increase this concentration of oxidant or oxidizer in the solution, you are going to increase this one. If it is at 1, no problem, reduction potential would be equal to the reduction potential at standard state. But if you keep increasing the oxidizer, and let us say if you have started the concentration of oxidizer in the solution at much lower value, and if you keep increasing this, this potential will keep moving up. So, initially I have started with this some concentration where my potential, this potential is basically nothing but this. Why I start with this at some particular concentration, and I have to see where my cathodic polarization line is cutting the anodic polarization line. So, accordingly this would be my I core, and let me plot that at this point. This is, let us say, corrosion rate, core rate as a function of concentration, as a function of concentration of the oxidizer. So, this is my I core, and core rate is nothing but the current density I can also have, because I core proportional to corrosion rate. We have already proved that, and there is some will be a constant term with this. So, now that point, let us say it is coming here. Let us say this is my point, correspond to this, let me put it as 1. This is my 1. Now, as I increase the concentration of oxidizer, my potential is gradually lifting, and then from that point, and I0, let us assume that I0 is not changing, I0 will remain same at the level, because we are not changing the metal. That now it will also have its parallel polarization, concentration parallel activation polarization for the cathodic reaction. So, this is point number 1, this is point number 2. So, I see that concentration corrosion is increasing. So, this would be my point number 2. Now, I can have a situation where I increase the concentration of oxidizer in such a manner. So, polarization line is cutting this anodic polarization curve at this point, where I attain, which is the current corresponds to I passive, and it is just crossing, it is a kind of tangent to this curve at this point. So, in that case I will see, because I have started with a freshly prepared surface, so it cannot reach there, rather it will remain here, because I do not have the formation of passive layer. So, my corrosion rate, let us say this is my point, corresponds to 3, my corrosion rate would be, let us say 3. Again I can use it further. So, I cut this line at 3 different positions, 1, 2, 3, one is passive zone, one is unstable passive zone and one is zone. And since we have started with the freshly prepared surface, it will remain here, because it cannot remain here, because either it can go there or there, because this is unstable zone. But since we have started with the passive since we have started with a freshly prepared surface where do not have any existence of oxide layer, so it will remain here. So, my corrosion rate again further increase. So, this is the point corresponds to 4. So, this is my 4th point. Now, I raise this concentration in such a manner or cut this point, cut this anodic polarization line in the critical zone. So, that time I will have this point as well as this point, but since we have started with freshly prepared surface, at this point I have that equilibrium between the rate at which oxide layer is forming and the rate at which metal dissolution is taking place. So, this point is still unstable. So, I can have still this I cannot reach there, because since it is unstable zone I will reach here, because we have started with freshly prepared surface. Again my corrosion rate increases. So, this is my 5th point, which corresponds to 5th, which corresponds to I critical. Now, beyond that, if I increase the concentration little bit, I can bypass this point. Once I bypass this point, I see that the current cathodic polarization line is cutting the anodic polarization line curve at this point, which is the stable passive zone. So, now see here it was the earlier case, it was here, which corresponds to 5. Now, once we reach to this level of concentration, I am seeing that the corrosion current or the rate of corrosion is in the passive zone, and this is my I passive equal to I core equal to minus I c. And I see that from here to there will be huge drop in the current density corresponding to the corrosion current density. So, my corrosion rate would come down, it would come down to a large extent. It will be here, because it will, this value is much lower than this value. So, it will drop here. And after that, if we increase the polarization concentration, I will cut this line at these points. So, this is my, let's say, point number 6, 7, 8. So, up to 8 I see that it is cutting the anodic polarization in the passive zone. So, from 6 to 8 I will have a constant current density for corrosion. So, I am not changing the current because it is on the vertical line with respect to the log I axis. So, this is my 6th point, this is my 7th point, this is my 8th point. So, I will connect this all those points, and I see that my corrosion rate is varying like this if you have started with freshly prepared surface. Now, if you increase it further, now you see from this to this, let us say this is my 9th point where it cuts the cathodic polarization line, cuts the anodic polarization, I see that there is increase in corrosion rate. So, my corrosion rate point, this is my 9th point, see that from here to there my corrosion rate is increasing from this to this. So, my corrosion rate would increase. Now, if I increase the concentration further, I will cut the line, this is 10th point, this is my 10th point. So, I have, this is the variation of corrosion rate. Now, let us say I will get back. Now, initially I increase the concentration, now let me decrease the concentration from this point onwards. If I decrease the concentration as the way we have increased the concentration of the oxidizer, it will also follow the same track. Now, let us say I increase the concentration in such a way the line polarization concentration cathodic polarization line is following this track, then I will get back to ninth position, which is corresponding to the corrosion rate. Now, if I get back to 8th, I will come to this. If I get back to 7, by decreasing the corrosion rate, decreasing the oxidizer concentration of oxidizer, I will get back to this. Like this, I will go up to 6th. Up to 6th, let me go back. Now, once we have this, let us say I have come back to the concentration corresponding to this line. Now, there is an important phenomena that is going on. When you are coming back from this to this, I am getting back to the passive region. So, if I am in the passive region and it is completely covered, then it will, in this case, it will remain here, it will not reach there, because already we have the passive zone, passive film. So, it cannot break like this. So, here it cannot break. So, it will, the passive zone will remain, or passive layer would remain, and the corrosion rate would be at this point, because it cannot reach there, because we have already have the passive layer. While we started from here, then as we moved gradually, so up to this point we did not have any passive layer, but when we are starting from top, we are up to this point, we are having, at this point also we are having the passive layer. So, it will remain here, the corrosion rate will remain here. So, 5 situation, in case of 5 also it will remain there. What would happen to the 4? So, 4 also it is cutting at 3 positions. Now, since we are cutting at stable zone, either go there or there, but since we have started, we have already the existence of passive layer, it will remain here. My corrosion rate, that case will come correspond to the 4 position, it will come here. Now, gradually if I go to the 3rd level, it will still remain here, because I am here, its I passive is just touching. So, I can still remain there. My corrosion current while going, it is following this track. While coming, this is following this track. This track. Now, once we come to this level, we see that only at this zone and active zone. So, that case the passive layer will break and it will get back to this point. And then if you again decrease, it will follow this track. So, while going, it is following this track, while coming, this is following like this, but at this point we are still having the passive layer, it will remain passive, and when we are reaching to the 2nd level, the concentration corresponding to this line, the passive layer is broken, and I have the corrosion rate which will reach to the 2nd level. And accordingly, if I go back to this concentration which corresponds to this line, then it will come back there. Okay. So, that means depending on your situation where from you are starting, if you are starting with a freshly prepared surface, you have to see where we are attaining the complete passivity, and if you are starting with passive layer, already passive layer, then we have to see where we completely remove the situation where we do not have any cross linking or crossing of this cathodic polarization line with the anodic polarization line in the passive zone. Fine, there we will go back to this point. Now, this exactly happens in the Faraday's situation, Faraday's experiment. What he did, initially you have concentrated HNO3, you have put iron surface, in that case it is attaining passivity, and that thing you are taking it there and you are putting it in concentrated in dilute HNO3, it does not have any reaction. So, what is happening, actually you have reached to this level, and now whether you decrease concentration of oxidizer, it does not matter, because you are already having the passive layer. But now what happens, let me give one small note here. Say at position 5, this corresponds to this corrosion rate, let us say, let me put it as 5 dust, this is 5 dust. So, while coming back it will remain here, but at this point let me give a scratch on the metal. If I give a scratch, if I put a scratch on the metal, what would happen? Now we have exposed the passive layer and we have exposed the fresh surface of the metal. So, that case it will no longer remain in passive region, it will go back to this. So, if it is scratched, it will go back to this, then mean from 5 dash to 5 it will reach. Let us say in case of this level of concentration, if I put a scratch, then from here it will move to this space. So, that case it will move this level. So, like that the scratch effect also is coming in the Faraday's experiment, where if you second case same dilute HNO3, you put the sample iron passivated iron piece with some scratch, you will see that vigorous bubbling is forming, because now you are no longer remaining in the passive zone, rather you are going to the active. So, this is the effect of oxidizer on the corrosion rate of active passive metal.